Namaskar. Today's topic is parallelogram law and its applications. And as per syllabus, this is for the students of M.Sc. Maths 4th semester, functional paper, functional analysis 4C6. So in this today lecture, we discuss the parallelogram law, polarization identity, and closed convex sets and their application, and some theorems based for closed convex sets. So first we see the theorem 1, that if x and y are any two vectors in a Hilbert space H, then the first one, the part A, is parallelogram law, that tells us that norm of the x plus y square plus norm of the x minus y square equal to twice norm x square plus twice norm y square. So this is known as parallelogram law. The second identity is known as polarization identity. This tells us that norm of the x plus y square minus norm of the x minus y square plus iota norm of the x plus iota y minus iota norm of the x minus iota y square equal to 4 times xy. Here xy denote the inner product is defined in the Hilbert space H. So if H is a Hilbert space, then we are having these two properties or identities. First one is parallelogram law and second one is polarization identity. Now we will see the proof of them. So for the part 1, part A, parallelogram law, we consider this norm of the x plus y square by definition of inner product and norm, that this is equal to x plus y comma x plus y inner product. Then opening this, we obtain this as norm x square plus x comma y inner product plus inner product y x plus norm y square. Similarly, norm of the x minus y square equal to inner product x minus y, and this is equal to norm x square minus inner product xy minus yx inner product plus norm y square. So we add these equations 1 and 2, then we get the desired result, that norm x plus y square plus norm x minus y square equal to 2 norm x square plus twice norm y square. So this is the proof of parallelogram law. Now we will see the proof of polarization identity. So its proof is little bit lengthy. We consider here norm x plus y. From the subtract the equation 2 from 1, and we obtain norm of the x plus norm x plus y square minus norm x minus y square equal to 2 inner product xy plus twice inner product yx. So we denote this by the equation number 3, and now we will take iota y in place of y in 3. So we obtain that norm of the x plus iota y square minus norm of the x minus iota y square equal to twice x iota y plus 2 iota y x equal to twice iota bar xy plus 2 iota yx, and then this will become minus 2 iota xy plus 2 iota yx, and this we denote by equation number 4. So multiplying this equation 4 by the iota, we obtain this as iota x plus iota y minus iota x minus iota y norm square equal to twice inner product xy minus 2 yx, and this we denote as equation number 5. So adding these equations 3 and 5, we get the desired result, polarization identity, this one. Now we prove a theorem that if x inner product of xz equal to yz for all z belongings to H, this implies and is implied that x equal to y. So we prove this that xz equal to yz. Then so we first let x inner product of the xz equal to inner product of the yz. Then we take this yz left hand side and obtain xz minus yz equal to 0, and applying the linearity of inner product we obtain this as x minus y comma z equal to 0. This result is true for all z belongings to H. So in particular we choose z equal to x minus iota y. Then we obtain this as x minus y inner product x minus y, and this here equal to 0. This is equal to 0. The inner product of x minus y equal to 0, and then this implies norm x minus y square equal to 0, and then by the property of the norm we obtain that x minus y equal to 0, and therefore this implies x equal to y. So we obtain that if xz equal to yz for all z, then x must be equal to y. Next, its converse part is obvious, that let x equal to y, then the result is obvious for all z belongings to H. Based on the polarization identity, we are having this theorem as theorem number 3. Let B be a complex Banach space in which norm obeys the parallelogram law and an inner product in B is defined by 4xy equal to norm x plus y square plus norm x minus y square plus iota norm x plus iota y square minus iota norm x minus iota y whole square. Then B is a Hilbert space. So if in the complex Banach space B we are having the parallelogram law and the inner product obeys this polarization identity, then B is a Hilbert space. So we prove this theorem. So we are consider the given result that we have given that norm obeys the parallelogram law in B, so that the parallelogram law norm x plus y square plus norm x minus y square plus equal to twice norm x square plus twice norm y square, and this we denote as equation number 1. And also it is given that for xy inner product equal to norm x plus y square minus x minus y norm square plus iota norm x plus iota y square minus iota norm x minus iota square, and this we will denote as equation number 2. So in order to prove that P will be a Hilbert space, if we show that the inner properties of the inner product or Hilbert space inner product defined by 2 satisfy the following three conditions. The first one, that H1 is XX inner product equal to norm x square and XY bar inner product bar equal to YX, and the third one AX plus BY comma Z equal to AX comma Z plus BY comma Z. So we shall prove them one by one in this way. For the property H1, to prove H1, replace y by x into we obtained 4xx equal to 4 norm x square minus norm 0 square plus iota 1 plus iota x norm square minus iota 1 minus iota norm square, and this will become 4 norm x square plus 2 iota norm x square minus 2 iota norm x square. So in this way we obtained that inner product of the xx equal to norm of the x square. This is the first property. Now for the second property, we start from 4xy bar, complex conjugate of this. So in the equation 2, we take conjugate of both the sides of 2, then obtain this equal to norm x plus y square minus norm x minus y square plus iota bar norm x plus iota y whole square minus iota bar x minus iota y whole square. Because norm of the x plus y is a real number, so we have omitted the complex conjugate sign on this norm. This is a real number. Then after simplification, we obtain this iota bar will be equal to minus iota, and this iota bar will be equal to plus iota, and from here we take outside the iota sign, and we are able to write x minus iota y norm equal to y plus iota x. Similarly, x plus iota y, and from here we take iota outside, then we obtain from this norm of the y minus iota x. So in this way we obtained that 4xy conjugate equal to 4yx. Therefore xy conjugate equal to yx. So in this way we obtained the property H2. Next we prove the property H3 in this way. Break this the property H3 in two parts. The first one is x plus y comma z equal to x comma z plus y comma z, and the second one is ax comma y equal to axy. So for this, replacing x by x plus y and y by z in equation 2, we obtain this inner product for x plus y z, this one, and we denote this by equation number 3. Now norm x plus y plus z square equal to norm of the x plus z plus y square, and this by the equation 1 parallelogram law, that this equal to norm x plus z square plus 2 norm y square minus x plus z minus y square, and this we denote as the equation number 4. And norm of the x plus z minus y square equal to norm of the z minus y plus x square, and this is again by equation 1. We obtain this as twice norm of the z minus y square plus twice norm of the x square minus x norm of the x plus y minus z square. So from 4 and 5 we obtained this as norm of the x plus y plus z square minus norm of the x plus y minus z square equal to twice norm x plus z square minus twice norm y minus z square plus norm y square minus twice norm x square, and this we denote as equation number 6. And interchanging x and y in 6, we obtained this, and this we denote as equation 7. Now we add these two equations 6 and 7, then we will obtain that twice norm x plus y plus z square minus this so on. So we obtain that norm of the x plus y plus z square minus norm of the x plus y minus z square equal to norm of the x plus z square minus norm of the y minus z square plus norm of the y plus z square minus norm of the x minus z square, and this we denote as equation number 8. Now we replace z by iota z in 8 and multiplying both the sides by iota, we obtain this, and we denote this as equation number 9. So now we use the equations 8 and 9 and add them, then we obtain the LHS of the sum is equal to the 4x plus y comma z by using the 2, and the RHS of the sum is equal to this one. So the first term, first part, this we can write as 4xz, and the second part we can write as 4yz. So we obtain that 4 of the x plus yz equal to 4xz plus 4yz. Therefore, we obtain the first part of this H3 property, that x plus yz equal to xz plus yz. Now we prove the second part, B part. So as proved in A, we obtain that x plus zy equal to xy plus zy, and take here z equal to x, then we obtain that this 2xy equal to xy plus xy equal to twice x comma y. So that is the result is true for A equal to 2. Now let it be true for a equal to n and a positive integer, that is nxy equal to nx comma y. So then we check this for n plus 1. Let then n plus 1 xy equal to nx plus x comma y equal to nxy plus xy, and then as we have used equation use equation 10, we can write this as n xy plus xy, and this is equal to n plus 1 xy. Then by the mathematical induction, we can say that this result is hold for all positive integers, that nxy equal to nxy. So hence by the law of induction, B is true for each positive integer a. Now we check for the if a is negative integer. So first we choose replace x by minus x into, we obtain 4 minus xy equal to norm x plus y minus x minus y whole square plus iota minus x plus iota y minus iota minus x minus iota. So I think here the minus sign will come. Here the minus sign, minus x plus norm y. Then after simplification, taking this minus sign outside, we obtain norm x minus y square minus norm x plus y square plus iota norm x minus iota y minus iota norm x plus iota y. Then taking minus sign outside, we obtain this, and this is the value of 4xy. So in this way, we obtain that minus xy inner product equal to minus x comma y, and this we denote as equation number 11. Now let a equal to minus b, where b is a positive integer. So then axy, then ax comma y equal to minus b x y equal to minus bxy, and then using the 11 we obtain this as minus bxy, and now as b is positive integer, therefore we can take this b outside, that is minus bxy, and value of minus b is a, therefore this is equal to axy. So we obtain that if a is any negative number, then we are having axy equal to axy. Now we check for the rational number, that when a is a rational, that is a equal to p by q, where p and q are integers with q not equal to 0. Then we have axy equal to p by qx comma y equal to pzy, where we put z equal to x by q is a vector. Here we put the vector z with value x by q. Then we can write this as pzy. Now p is the integer, so we can take this outside, and also qzy equal to q into z. So now we use these two results, that zy, that is zy equal to 1 by q qz. So now using the equation 12 and 13, we obtain that axy equal to p by q qz comma y equal to ax comma y, because a equal to p by q and qz equal to x. So similarly, we can prove that if a is any real number, then axy equal to axy. Now we check for the complex number, that if a is a complex number, so replace for this, we replace x by iota x into, we obtain for iota xy. So after simplification of this part, we obtain this as iota for xy, that is iota xy equal to iota xy. Therefore, this we denote as equation number 14. Now let a equal to a1 plus iota a2, where a1 and a2 are any real numbers. That is ax comma y equal to a1 plus iota a2, x comma y equal to a1x plus iota a2x comma y equal to a1xy plus iota a2x comma y equal to a1xy plus iota a2xy by 14. Then this is equal to a1xy plus iota a2xy equal to a1 plus iota a2xy equal to axy. So thus we obtain that axy equal to axy for each scalar a. Hence B is a Hilbert space. So we have proved all properties of Hilbert space. Therefore, H is a Hilbert space, and in which the inner product is defined by the polarization identity. Now we see the convex set and its related theorems. So first we define the convex set. Let L be a linear space, and a non-empty subset S of L is said to be convex if xy belongs to S implies lambda x plus 1 minus lambda y belongs to S, where lambda is any real number such that 0 is less than equal to lambda is less than equal to 1. Now for these closed convex sets, we are having two theorems. The first one is, theorem tells us that theorem number 4, that a closed convex subset C of a Hilbert space H contains a unique vector of the smallest norm. We see here the proof, that let D equal to infimum norm x belonging to C, then there must exist a sequence xn of vectors in C such that norm of the xn tends to D. Now let xn belongs to sequence xn, that is xm comma xn belongs to C, and as C is convex set, therefore xm plus xn by 2 belongs to C, and therefore norm of the xm plus xn upon 2 is greater than equal to D, that is norm xm plus xn is greater than equal to 2D. Then by the parallelogram, we obtain that norm of the xm minus xn square equal to twice norm xm square, plus twice norm xn square minus xm plus xn norm square. So then by using the equation 1, we write this quantity as 4d square, which is less. So then this is equal to 2xm square plus 2xn norm square minus 4d square, and as xm x and xn tends to d, as mn tends to infinity, then this becomes 2d square plus 2d square minus 4d square. Therefore, this tends to 0 as mn tends to infinity. Hence, Xn is a Cauchy sequence in C, and as C is complete, being a closed subset of a complete space of H is complete. Therefore, there exists X belonging to C such that this sequence Xn tends to X. That is, no norm X equal to limit of the Xn norm equal to limit norm Xn, because norm is a continuous function. So this is equal to D. Hence X is a vector in C with the smallest norm D. Now we prove the uniqueness of the X. And for this we consider let X and X dash be two such type of vectors in C such that norm of the X equal to D and norm of the X dash equal to D. Then now x dash belongs to C, therefore x plus x dash by 2 also belongs to C because C is a convex set, and then this implies that norm of the x plus x dash by 2 is greater and equal to D, and that is norm x plus x dash is greater and equal to 2D. This we denote as equation number 3. And now by parallelogram law, norm of the x minus x dash square equal to twice norm x square plus twice norm x dash square minus x plus x dash. So now use the equation 2 and 3 we obtain, right, can write this is less and equal to 2d square plus 2d square minus 4d square, and this is equal to 0. So thus we obtained that norm of the x minus x dash square less and equal to 0, and then this implies norm of the x minus x square equal to 0 because norm is non-negative quantity, and then this implies x minus x dash equal to 0 or x equal to x dash. So therefore x is a union. So in any closed convex subset, we are having a unique element of the smallest norm. Similar to this theorem, we are having the last theorem number 5. This statement is let M be a closed linear subspace of a Hilbert space, and let X be a vector not in M, and D be the distance of X from M. Then there exists a unique vector y0 in M such that norm of the x minus y0 equal to D. Now by definition of the distance, D equal to dxm equal to infimum norm x minus z such that z belongs to M. Then there must exist a sequence yn in M such that norm of the x minus yn tends to D, and now we let mn yn belongs to sequence yn, that is yn belongs to M, then this implies ym plus yn by 2 belongs to M because M is a subspace and this is a convex set. So then this implies norm x minus ym plus yn upon 2 is greater and equal to D by definition of the D, and then this implies norm 2x minus ym plus yn greater and equal to 2D. Now by parallelogram law, that x minus yn minus x minus ym square equal to this one, twice x minus ym square plus twice x minus ym square, and so on. So in this way, we obtain a norm of the ym minus yn square tends to 0. As mn tends to infinity, here are using equation. So therefore, yn is a Cauchy sequence in M, and as M is complete, so being a closed subspace of a complete space, H is complete. Therefore, there exists y0 belonging to M such that yn this sequence tends to y0. Now x norm x minus y0 equal to norm x minus limit yn equal to limit x minus yn, and this is equal to limit norm x minus yn to d. Hence y0 is a such vector in M such that norm of the x minus y0 equal to. Now we prove the uniqueness of this y0. So for the uniqueness, let y1, y2, where y1 is not equal to y2, be two vectors in M such that norm of the x minus y1 equal to d equal to norm of the x minus y2. Then we have to show that y1 equal to. Now y1, y2 belongs to M, therefore y1 plus y2 by 2 belongs to M because M is a subspace. So then this implies norm x minus y1 plus y2 upon 2 is greater and equal to d by definition of the 2. Then we take 2 this outside and this side. So we obtain norm 2x minus y1 plus y2 is greater and equal to 2d. This we denote as equation number 2. And now by parallelogram law, norm of the x minus y1 minus x minus y2 square equal to twice x minus y1 norm square plus twice norm x minus y2 minus x minus y1 plus x minus y2 square. Here square square. So then using the equation number 2, we obtain this as equal to 0. Therefore, norm of the y2 minus y1 square is less and equal to 0. And then this implies that norm of the y2 minus y1 square equal to 0 because norm is a non-negative quantity. And this implies y2 minus y1 equal to 0 implies y2 equal to y1. Therefore, y0 is. So in today's lecture, we have studied the parallelogram law, polarization identity, convex set, closed convex set, and these two theorems that each closed convex set contains unique vector of smallest norm. So for the more detail, students can read, refer book of functional analysis. I am Dr. Rpsomani, Associate Professor in Mathematics. Thank you.